So next up we have the one and only Brandon. Brandon is also a former Objective-C speaker. He's always doing incredible iOS security research. Jonathan Levin, who's one of the top security researchers in the field, always has incredible things to say about Brandon, which are fully 100% true. Right? Right.
He's very kind. People are very kind.
No, it's so we are really happy to have Brandon talking about some incredible research he's done and a really amazing iOS debug that he recently found that for the first time at the conference he's going to be publicly discussing. So round of applause for Brandon.
Hello, everyone. My name is Brandon Azad. I work at Google Project Zero, and I'm going to be talking to you about a research project that I undertook starting actually almost a year ago now, going up to about August of last year. And the basic idea of this project is to build what I call the debuggable iPhone, some device which would allow me to get low-level debug access to the iPhone. And to kind of understand what this project is all about, I need to take you along talking about something which usually isn't all that well discussed, at least publicly. So there's this thing that many iOS security researchers, most not, but some iOS security researchers have access to, called dev-fused devices, development iPhones. These are basically special iPhones that have debug capabilities built into them. So things like JTAG, serial wire debug. This is not just your normal LLDB connects to a phone. This is like special dedicated hardware that's only supposed to be available to Apple engineers in order to do very low-level debugging of the operating system, of the bootloader, very low-level access. So these devices are not obviously sold by Apple. This is a picture from a Vice motherboard article about these devices, and people are able to obtain them using various means. And when you have access to them, you can do various low-level analyses of the device to find vulnerabilities that maybe are much harder to find if you don't have this low-level debug access to the operating system. Now, in order to actually drive the debug hardware on the phone, you need a special type of cable, often called a probe. Here is an example of what's called a CONSI probe. So this has a special lightning connector on one end, and then there's a chunky part in the middle which contains a controller that drives the interface to the hardware. And then on the other end, you have the regular USB port, which you can plug into a laptop. And using special software, you can connect to this probe, operate it, and drive the debugging hardware on the phone to do like breakpoints, watch points on the phone in the operating system and the bootloader, what have you. So again, these are not cables which are sold by Apple. Some people are able to acquire them. And the software that's used to drive these probes is something called Asterisk. This is a piece of Apple internal software. Again, they don't make this public. This is like leaked software that people are able to obtain. Here is an example of someone using Asterisk with a Kong serial wire debug probe. And they have halted execution inside the bootloader and dumped the 32-bit register state. So let's see. So these registers right here is the 32-bit register state. And you can see that they've saved the memory contents to this iBoot file. So presumably they're dumping iBoot in order to get a decrypted copy of Apple's bootloader for security vulnerability research. So I do not use these dev-fused devices. I don't have access to them. I don't want to have access to them. There are various complications surrounding them. I'm not going to touch them. But nevertheless, it would really make my job a lot easier if I did have access to these devices. Part of my job at Project Zero is I try to find vulnerabilities in the iPhone and report them to Apple. And having the kind of lack of debug tooling available really makes my job that much harder. I have, in some ways, a disadvantage to compare to people who do have these debug devices. So that's kind of the motivation for this project, is I wanted to basically find a way to build a similar capability a debuggable phone that is totally legit, totally off the shelf that I could use for my day-to-day work at Project Zero. So the goal was to build my own homebrewed development phone. And I kind of outlined 5 capabilities that I really wanted this project to achieve. First, I wanted the ability for this homebrewed dev phone to be able to patch kernel memory, and in particular, be able to patch the executable memory in the kernel. And we'll get back to why this is actually a hard thing to do just very quickly. The next feature, kind of important for any debugger, is the ability to set breakpoints and watch points. I wanted it to be possible to use with off-the-shelf debugging software, so LLDB, IDA Pro, so you don't have to use Apple internal software like Asterisk in order to operate it. That's bad. I wanted it to be possible to update the version of iOS on the phone so that I can, if I'm going to spend 6 months investing in this development project to build a iOS kernel debugger, I don't want to only be able to debug one version of iOS. I want it to, amortize the development cost across multiple versions of the operating system. So that might mean finding a hardware vulnerability, that might mean finding a bootloader vulnerability, but basically a kernel vulnerability alone would not be sufficient, because then once Apple patches the kernel bug, my debug capability goes away. And finally, kind of the key part of this whole project is I wanted to build this debuggable iPhone using only parts you can get at an Apple store. So no specially fused CPUs, no special debug probes, nothing like that. So just, go into an Apple store, buy everything you need there. This is actually a strictly more powerful capability. Everything that I set out to accomplish in my project is totally accomplished by Checkmate and the Checkbrain project. And in fact, many of the features that I put into KTRW may make their way into the standard Checkbrain project itself. So even though this research came out and is more powerful, and I expect future tooling to be built around this instead of the capabilities that I found, this capability didn't actually exist when I started my research project. So many of the assumptions that I had going in no longer hold now, but did hold kind of at the point I was doing this research. So just to clarify that part. All right, so let's talk about what makes kernel debugging on iOS really, really difficult right now. And this is this thing called KTRR. So if you remember from a slide earlier what I wanted out of this debuggable iPhone project, one of the very first things that I mentioned was the ability to patch kernel memory, and in particular, to patch the kernel's executable code. If you can do that, that means that you can run shellcode in the kernel, and that's a really useful feature to have for debugging and analyzing the hardware. And Apple has basically done a very good job trying to make this step in particular extremely difficult. So if you look at the kernel in memory, so the actual kernel is often referred to as the kernel cache because it contains both the kernel's code and all of the drivers that are prepackaged into it. And here you can see kind of a representation of how it's laid out in kernel memory. And it's composed of a number of different segments. So you have some data which needs to be read-writable. So, global variables which get updated, global pointers to lists, things like that. So this data is included in the kernel image, but it does need to be updated dynamically. So that has to be read-write. But there's also a lot of data which really does not need to be writable at runtime. So for example, we have executable code is kind of the most obvious example of that. So of course, if you can patch the kernel's executable code, that's really bad for a security standpoint. But you also have a number of other pieces of data which are not quite as critical. You don't need them to be interesting. No worries. We'll steam on ahead. So there's a number of other pieces of data which are, we want them to be read-only, but not executable. So you still want to be able to protect them. But you also want to make sure that they don't get executed. So things like strings, no reason to change those. Virtual method tables probably should be const. Page tables, this section called pints, which is privileged instructions or protected instructions. So things like that are just really should stay read-only. And so what Apple has done is they've implemented a mitigation called KTRR, which is designed to lock down these read-only segments of the kernel cache and make sure that those segments really do stay read-only, and you can only execute stuff inside of that region. So kind of from backing up a little bit, what is KTRR? We think it stands for kernel text read-only region. We don't actually know. And it basically boils down to a really strong form of write XOR execute protection. It's implemented in Apple A10 CPUs and later, and it provides two pretty strong guarantees. So the first is that all writes to memory inside of the KTRR region will fail. So that means that the region that's protected by KTRR is going to be guaranteed to stay read-only. And the second guarantee is that all instruction fetches from outside of the KTRR region will also fail. So that means the only memory that you can execute is that which has been protected by KTRR, which is guaranteed to be read-only. And kind of the idea is, well, if the bootloader has successfully put the kernel cache into memory, verified the cryptographic signature, and we have managed to get the secure boot chain to boot all the way up to the point where the kernel is loaded into memory, then KTRR is supposed to ensure that that integrity remains for the lifetime of the system. So once you have an iPhone that's running, you know that at any future point, the kernel has not been modified. It's still the same one that's been signed by the secure boot process. So it's a really interesting kind of security feature, a really nice extension of write XOR execute to kind of extend secure boot all the way through the lifetime of the system. So let's look a little bit about how KTRR actually might work under the hood. And now I don't know how it works in detail. This is kind of my guess and analysis, but it's reasonable enough that it's a plausible model of how it works. So here's a simplified diagram of an A11 CPU, which has 4 little CPU cores and 2 big CPU cores. The little purple boxes in there are the MMUs. So you can see you have 6 MMUs, 1 for each core. You have the highest level of cache hierarchy is the L2 cache. And then you also have the memory controller, which lies behind the L2 cache. And also behind the memory controller, you have DRAM, which holds the physical pages. So the kernel is going to be loaded contiguously into a certain range of physical memory. And Apple's goal is to basically lock down those specific pages of physical memory with KTRR. So this becomes the Ktr Protected Region. So in order to understand how this protection is enforced, let's zoom in on a single CPU core. What Apple's basically done is add 2 registers to the MMU. And these registers are going to point to the beginning and ending address of the KTRR lockdown region. And what this allows us to do is the CPU can now really quickly check whether each instruction that gets executed is going to violate the security properties of KTRR. So for example, let's say that the CPU tries to issue a write, and that write falls outside of the KTRR region. That is allowed to succeed since it doesn't violate the KTRR security principles. If, on the other hand, there's a write which hits inside of the KTRR region, then it's very quick for the MMU to check, hey, this falls inside the bounds of these 2 registers, so it's going to deny the write and cause that instruction which generated the write to fault. Similarly, if you try to execute memory outside of the KTRR region, the MMU can really quickly see, hey, this doesn't look valid, it's going to fault, and you're not going to be allowed to execute memory outside of the protected region. So that's kind of what the new picture of the CPU looks like with these additional registers in the MMU to kind of enforce the KTRR security properties on the actual CPU cores themselves. But unfortunately, this isn't the full picture for protection. And the reason is because this CPU isn't the only place that can issue writes to the memory controller. In particular, there are a number of other devices on the system, peripherals like the Wi-Fi chip, which can also issue writes directly to the memory controller, and they will eventually hit DRAM. So what Apple has had to do is they've added the lockdown registers to the AMCC as well, so that now the memory controller knows the beginning and ending bounds of the lockdown region, and anytime a write from a peripheral, like let's say someone's compromised your Wi-Fi chip and bypassed the IOMMU, if that manages to hit the memory controller, KTRR is still going to be enforced because the memory controller will just discard that write, which would otherwise corrupt the protected region. And this is kind of the complete picture of, the simplified complete picture of how KTRR has been implemented on the A11 CPUs. There is one other thing which we need to address, which is that while the system works very well in practice, there's a lot of kind of nuances which need to be handled correctly in the software. and in particular around what happens when a core goes to sleep and then wakes up. See, when a CPU core goes to sleep, it's going to enter this deep sleep state, and it's going to lose the state in all of its registers. And in particular, the MMU lockdown registers are going to lose their values. So if KTRR only lasts until the first time a CPU sleeps, that's obviously not very useful since sleeps happen all the time. So Apple needed to add code to make sure that every time a CPU core wakes from sleep, it reinitializes the registers on the MMU and relocks down KTRR. So the piece of code which XNU executes when it wakes from sleep is called the reset vector. It's called low reset vector base in the source code. And this is basically a disassembly of the first couple of instructions in the iOS 12.4 kernel cache for the iPhone 8, which you can see kind of at the start, you had some initialization code, and pretty soon in, there's some code which does lockdown. So these two global variables, read-only region begin and read-only region end, are variables inside of the locked down region itself, and they contain the addresses of the beginning and ending of this lockdown region. And what happens is the reset vector will very quickly read these values into registers and then write those values to these special system registers using MSR instructions. And so this is the actual point at which the beginning and ending bounds on the MMU are set and established, and then that MMU is locked down to make sure that these register values can't change, and KTRR is then enabled. All right, so that's kind of an overview of how KTRR works on the iPhone, and now let's look at how to break it. In order to do that, let's first look at kind of a historical perspective, since this isn't the first time that people have tried to bypass KTRR by any means. So the first public bypass of KTRR came in iOS 10.1.1, which was when Luca Tedesco found that Apple had accidentally left an instruction, the MSR TTBR1 instruction, executable in the kernel cache. The TTBR1 register is used to store the root of the page table hierarchy for the kernel's half of the address space. What this means is that Apple had basically left in an instruction which, if you executed it using return-oriented programming, would let you set a new root for your page table hierarchy and remap the kernel onto different pages. So this is bad because that basically means that KTRR is locking down a certain set of physical pages, but it doesn't protect any other physical pages. So if you set your kernel to be mapped onto different physical pages, it'll run just fine. And so this is basically what Luca did in his YALU KTRR bypass, is he used that TTBR1 instruction to set a new page table base, and basically, data in the kernel, which used to be read-only, is now writable. It's not a full bypass because KTRR is actually still initialized at this point. So the write XOR execute protections are still in place. You can't execute new code outside of the KTRR region, but the lockdown no longer applies to the read-only data that has now become read-writable. So kind of graphically, what this looks like is it used to be that all of this data was protected by KTRR, and by remapping the kernel, you've restricted what's protected by KTRR to only be the executable code. Now things like strings, virtual method tables, all of those are now writable as well. The other interesting bypass for KTRR came in iOS 11.1.2 when Ian Beer released a project called Build Your Own iOS Kernel Debugger. This project, unsurprisingly, was a large inspiration for this project. So Ian Beer found that the self-hosted debugging registers, which are part of the ARM specification, could actually be enabled on iPhones. So self-hosted debugging is a feature in the ARM architecture which allows a kernel to implement a debugger for itself. So if you've ever used like KDP to debug one MacBook with another MacBook remotely over UDP, it's kind of a very similar principle to that. The kernel kind of catches its own exceptions, catches its own, anytime it faults, it catches that, and then it farms that out and says, look, this event has happened. We'll let a debugger that the kernel itself implements handle that and decide what action needs to be taken accordingly. So what Ian found was that it was actually possible to enable self-hosted debug using return-oriented programming to access specific gadgets which set those registers. And using this, he was able to build a fairly full-featured iOS kernel debugger that supported things like breakpoints for iOS 11.1.2. So it's important to note that KTRR is actually still fully enabled in this setting, so it's not a full bypass in that sense, but it is kind of a bypass in principle in that you can execute instructions in arbitrary order by setting a breakpoint, executing a single instruction, jumping to another instruction, executing that instruction. So the linear sequence of control flow that is necessary for return-oriented programming, that's totally gone. You can execute single instructions all over the place. So kind of with an understanding of what the historical attempts on bypassing KTRR were, I decided to look at how I would bypass it for this kernel debuggable iPhone project. And I basically identified a number of different areas which looked promising and investigated each in turn. The first thing I looked for was if there was a bug in iBoot, in particular in the image 4 processing code. I looked for a month or so and didn't really find anything interesting. I next looked at, maybe reading the ARM specification. There looks like there might be some interesting stuff where if you set page tables in a certain way, maybe you could get TLB entries to behave really weirdly, but that didn't end up panning out. I also looked at some other, maybe there were ways to corrupt L2 cache entries by mismanaging state. That didn't pan out either. So nothing that I really looked at ended up making the system behave in a weird way that led me to think that, maybe there's a way to bypass KTR down this avenue. So I eventually, a lot of research didn't pan out, so I kind of put this on the back burner for a while and didn't really think about it for a couple months. But eventually, I saw something kind of interesting which brought this project back to the forefront, which is that I'd managed to get a really weird panic message to happen on my iPhone. So I was playing around with interrupts, and I managed to get a CPU core stuck in the kernel in an infinite loop with interrupts disabled. And when you get into this weird state, basically, nothing can preempt this CPU core and make it execute anything else because interrupts are disabled. So the way the system detects this is it'll say, hey, look, CPU core number 1 hasn't checked in with the watchdog timer in 5 seconds, so probably it's really stuck in an infinite loop, so we're going to panic the system. And that's exactly what you see in this panic message. It says, panic, watchdog timer timeout, CPU 1 failed to respond. But what caught my eye about this panic message was actually something a little bit earlier on, which I'd noticed but not really paid attention to before. It said, attempting to forcibly halt CPU 1. And this was really interesting to me because forcibly halting a CPU, as far as I was aware, there wasn't a way to do that in kind of your standard ARM architecture. There wasn't like an instruction that you could execute that was like halt CPU, halt a different CPU. There's no instruction that does that in the ARM architecture. So I was like, this seems kind of weird. I don't really know how this would be implemented. Maybe, there's some sort of custom CPU control register involved, accessible via MMIO. I don't really know, but it seemed really interesting and certainly not something I've ever seen before. So might as well kind of dig into this and see what there is there. So in order to do that, I pulled up the most useful security research tool that exists, which everyone say it with me, grep. So I basically grepped through the XNU source code and found this string attempting to forcibly halt CPU. And this really quickly brought me to this function, which was ml debug grep halt CPU. This function takes the index, so 0 to 5, of the CPU core that you're trying to halt. And the implementation is a little bit lower on, where we have this volatile integer type debug grep reg. And the actual act of halting the CPU core simply consists of writing this value debug grep halt to the address pointed to by debug grep reg. So this is really interesting. The fact that we're dealing with volatile memory and performing an action simply consists of doing a single write really strongly suggests that we have some sort of MMIO register here. So there's memory mapped, memory mapped physical address, and when you issue a write to this physical address, it causes the hardware to perform an action on your behalf. So this really looked promising, as there really looks something interesting here. I haven't seen this before. And kind of the name itself, debug grep, I don't know what grep stands for, but debug, I've heard the name debug before, so it seems worth investigating. And the other thing which was kind of interesting and caught my eye was references to Coresight. It seems like this debug wrap variable is read off of a per CPU data structure as part of this Coresight base array of pointers. So whatever this Coresight is, maybe it's kind of the technology that provides this debug wrap thing. I didn't really know at the time, but definitely seemed worth investigating. But really the most interesting feature that I found while I was reading through this code was a function just a few lines down, which was called ml debug wrap halt CPU with state. So this is a very similar function to ml debug wrap halt CPU. It again takes the index of the CPU you want to halt. But the main difference between this one and the old function is that this function, in addition to halting the CPU, also gives you the state of the halted registers in a state data structure. So it's supposed to fill out, xi contains the numerical value of register xi at the point that it was halted. So really, really interesting. I didn't know how this could possibly be implemented, but digging through, I kind of found two interesting points. So here you can see there's another reference to these memory mapped Coresight registers. So that definitely seems like something important to do with Coresight. But then the actual implementation of this function is what's really, really fascinating. And so here you can see that there's a loop over all the indices of the general purpose registers. And it does the following steps. So the first thing it does is it builds the numerical opcode of this MSR debug DTR XI instruction. So the MSR debug DTR XI instruction is going to move the value of register XI into the special system register debug DTR. But this isn't actually the opcode inside of the code. This is building the numerical value of that opcode. It's like building the number of the instruction that you would want to execute, but it doesn't actually have that instruction present in the code. It then passes the numerical value of that opcode to this function ml debug wrap stuff instruction. And then afterwards, it calls the function ml debug wrap read DTR to read the value of debug DTR, and it stores that in the state variable xi. So what this really, really strongly suggests is that the ml debug wrap stuff instruction function is actually executing dynamically generated instructions. And this is really, really interesting because it flies in the face of the KTRR security model. If you think of KTRR as a way to lock down what instructions can be executed in Apple's kernel, such that only the instructions that are signed by secure boot, those are the only ones that can be executed. Well, here we have a function which is just like, give me an opcode and I'll execute it for you. So this is really, really weird. It's very unexpected, not something which, makes sense under the KTRR security model. So I think, really definitely a very promising avenue for a KTRR bypass. But just because a piece of code exists in the XNU kernel doesn't mean that that code actually works. So the only way to find out is to actually run the code and see, does this function actually work? So I did an experiment. I basically took an exploit that I'd previously written, a kernel exploit that gave me the ability to call kernel functions. And I extended it with a bit of code that would just call this kernel function ml debug wrap halt CPU with state from user space. And when I call this kernel function, it's going to pass in the address of some in-kernel buffer. And then I would read out the output value of the buffer after the function returns and dump it to see, did it actually look like I halted a CPU and dumped out its registers. And what I found was somewhat surprising, but it kind of looked like it did actually work. So in particular, the value of CPSR right there, 6003C5, really, really looks like a valid CPSR value. And in particular, it looks like a CPU core that's executing in kernel mode with interrupts disabled. Now, the PC value doesn't really match a kernel pointer. You would expect the first couple digits to be all like FFFF in that case. But it does look a lot like a physical address, which is kind of wild. And so I took the kernel slide, calculated what this address would be in the static kernel cache. And what I found was that this is actually the address of an instruction in the reset vector. What this means is that we've managed to actually halt execution of a CPU core inside of the reset vector, and in particular before the MMU has been turned on. And because KTRR only takes effect once the MMU has been turned on, that means we've managed to halt the CPU before KTRR has been locked down. So at this point in time, where the CPU core has been halted, KTRR is not blocking us from scribbling all over the protected memory region. So this is really, really cool. So how are we actually going to use this to bypass KTRR? It seems really promising, but we're not quite there yet. And really the key to figuring out how to bypass this is we need to understand what this Coresight thing that we keep seeing references to is. So a little bit of research, if you dive into the ARM architecture manual for ARM v8, you'll see there are a number of references to Coresight. In particular, you'll learn that there's a memory mapped external debug interface, which is basically, if you remember Ian Beer's Build Your Own iOS Kernel Debugger project, Ian Beer was using the self-hosted debug interface. And Coresight, what we're seeing here is the external debug interface, which is kind of the memory mapped version of that same interface. So it's, for the most part, the same debugging hardware under the hood. It's just accessed in a different way via MMIO or via an external debug port rather than by the kernel executing special instructions to drive the debugging hardware. So very promising. If we can access the same debugging interface that Ian used, but via memory mapped IO rather than via executing special instructions, then it doesn't even matter that Apple has removed the instructions that Ian used in his return-oriented programming, since we can create those same effects just by writing to memory regions. And definitely this is not by any means the first time that anyone has used the external debug interface to do interesting things, violate privilege barriers on systems. So at MOSEC 2019, there was a presentation on the nail gun attack, which is a way to extract fingerprint data from trust zone on certain ARM devices. And this is clearly demonstrates that using Coresight to do stuff like this, violate privilege boundaries, is totally possible in practice, and has been done for ages and ages, both publicly and privately. So kind of summarizing the Coresight external debug interface, it's an on-chip debugging architecture. There are per CPU debug registers which are accessible via MMIO, and it's really extensively documented in the ARM manual, so I'm not going to go into all those details here. But what I will say is that it does give you all the functionality you would need to build a kernel debugger, including the ability to set breakpoints and watch points, the ability to execute arbitrary instructions, all that kind of stuff. And it is, in fact, the memory mapped version of the debug registers used in Ian's Build Your Own iOS Kernel Debugger project. So very promising for us to bypass KTRR. And the idea that I had to use the external debug interface was to basically single-step execution of the reset vector and skip the point at which KTRR is locked down. So hypothetically, you could set a breakpoint at the very beginning of low reset vector base and just do, figure out how to do single stepping and single step through all of these instructions until we get to this conditional branch instruction right here. And then, change the register state at this exact point to make x17 0, and then we'll take the branch and skip over the KTRR lockdown code, leaving KTRR uninitialized and unprotected on the MMU. But we don't quite have enough to do that at this point. We have the ability to halt a CPU core, and we know that we can execute instructions on it, but we still don't know how to resume execution after having halted a CPU and done our modifications. So, if we manage to halt the CPU in the reset vector, that's still not a ton of use to us, and we can't then resume execution afterwards, because then we're just going to be stuck in the reset vector forever. And similarly, we know that we can use one CPU core to hijack a second CPU core as it's executing the reset vector. But if we have to do that every single time a CPU core resets, that's kind of a pain. Your CPU cores reset all the time. And if it has to happen every single time, what happens if all 6 CPUs reset at the same time and then you lose all of your bypass state and your KTR bypass is just gone at that point? That would be really problematic. So ideally, there would be some way to disable CPU cores from resetting, so we only have to bypass KTR once, and then it's just good to go from that point on. And it was actually turned out to be not nearly as difficult as I feared it would be to find both of these functionalities. So if you remember, there was the Coresight external debug interface, and also this debug wrap register, which is the first register that we found. The debug wrap register is not part of Coresight. It seems to be some sort of Apple custom thing, and is totally undocumented. But I basically just, did a ton of experiments, just setting random bits in this register to see what would happen. And just by sheer dumb luck, all the functionality that we needed to complete the KTR bypass is present in these registers. So we have the ability to set, I think it's bit 29 will cause the CPU core to resume, and a different bit will cause it to disable core resets, and then you're totally set and good to go. So the final KTR bypass basically looks like you single-step execution until you get to this branch instruction, and then take the branch to skip KTR lockdown. KTR registers never get initialized, and then your CPU core goes from looking like this with the MMU KTR registers in green being initialized to all of a sudden being disabled, which means that we now have the ability to execute kernel shell code. All right, so it's been kind of a whirlwind. Thank you. Basically, in order to build the kernel debugger, the first thing we need to do is remap the kernel to make it writable. Then we need to build a capability to load a kernel extension, since it would be really, really sucky to implement our entire kernel debugger in user space and do back and forth to the kernel while the debugger is debugging that same kernel. That's a huge pain. We need to make sure the interrupt handling is correct, because there's a lot of trickiness involved in making sure that when you're halting CPU cores, those happen in a very safe way. We need to establish some sort of communication channel between the phone that has the debugger running on it and your laptop, which is running like LLDB. And finally, we need to implement a GDB stub, which is capable of receiving commands from your computer and driving the debugger on the phone. So at the point we are right now, we've disabled KTR on the MMU, but KTR is still fully enabled on the memory controller. So what this means is that the pages that are still protected by KTRR are still read-only. We can't yet modify those specific physical pages. And this is really problematic because we need to be able to modify page table permissions in order to make our kernel extension, which we're going to put in the kernel, be executable. Because there's no text loading functionality that we can use out of the box in iOS. And in particular, the root page tables are in the KTR read-only region. So the root page table hierarchy is still read-only at this point. So the way to get around this is just like what Luca Tedesco did back in iOS 10.1.1. We can remap the kernel onto fresh writable pages and set TTBR1 to point to the new page tables instead. So looking at the system here, we have TTBR1 points to the root of the page table hierarchy, which is inside of the locked down region. All we do is we copy the contents of those locked down pages onto new pages, and then we update TTBR1 to point to the new page tables instead. And now we can just forget that those old pages even existed, pretend that memory has just been leaked and is gone, and now our kernel appears to be writable from the perspective of the kernel. At this point, it's pretty easy to load kernel extensions. We just allocate some memory for the kernel extension, copy in the binary of the kernel extension into kernel memory, dynamically link it against the running kernel, and then modify page table permissions to make it executable. And finally, we can call the cache start function inside the kernel extension to begin it running. And that's basically it for kernel extension loading. At this point, we can begin kind of designing the debugger itself. And so I settled on a very simplistic design just because it was such a huge pain to get this whole system working in the first place. I basically said, you know what, screw power consumption. I'm going to have one core, which is going to be reserved for the debugger itself. This is the monitor core. And then the other 5 CPU cores on the iPhone that are left, those are going to still run XNU as they do normally. So there is kind of, remove the performance hit for removing one CPU core that's reserved solely for the debugger. But as you will see, it gets a lot worse than that. So don't worry about the performance hit there. The other 5 cores are going to run XNU as they normally do. And when any of those cores hit a breakpoint or a watch point, that's going to cause that debugged core to halt and enter what's called debug state. Now in debug state, it's not going to, the CPU core isn't going to do anything, it's just halted and is waiting to receive commands from the monitor core. So the monitor core is going to sit in an infinite loop polling for entries from the other cores into debug state. And when it observes that, it's going to notify LLDB that this has happened over some as yet unspecified communication channel. Now, the result of this design is that you have one CPU core, which is kind of spinning in an infinite loop in the kernel with interrupts, most interrupts disabled. I think IRQs are still enabled. But the result of that is your phone will get physically hot and may burn you, so be careful. So yeah, we need some sort of communication channel for LLDB to communicate with the kernel extension running on your phone, because LLDB is on your laptop. So I considered a number of different communication channels. Each had, advantages and disadvantages. The advantage for serial is that it's a really easy protocol to implement. It's really easy to write a serial driver for hardware. USB I also considered because it's extremely fast compared to serial. The speed up is orders of magnitude better. So your debugging session will feel much more responsive. Wi-Fi I considered because it's another option, not really any advantages that I could see besides if the other two didn't work out, I could potentially do Wi-Fi. But in the end, it was the disadvantages which really drove the decision. So serial is pretty much eliminated right off the bat because it requires special hardware in order to communicate using serial to your iPhone. I did look into, there are some sellers of legitimate serial cables for the iPhone, and I tried to get those to work, but none of them really did. USB is a huge pain because it means you have to write a custom USB stack that's running inside of your kernel extension, which is separate from XNU's USB stack. And I really did not fancy writing a USB stack from scratch. And Wi-Fi, you also have to write your own custom Wi-Fi driver from scratch. So between those two kind of evils, writing a custom USB stack was like slightly better, so I went with that route. Now, the problem with the USB controller is that it is actually a reasonably well-known controller. It's by Synopsys. It's called the Designware High-Speed USB 2.0 on-the-go controller. However, the datasheet is actually protected by a sign-in wall, and I didn't have access to it. So I had to write a USB stack for this hardware without having access to an actual datasheet that told me how this hardware actually operated. And there were some open source header files describing how to operate this hardware, but I didn't find, during the course of this research project, I didn't find an open source driver for operating the Synopsys controller in device mode, which is what you would need to do for the iPhone. So in the end, I had no data sheet. I had header files describing, the offsets of the registers and the names of the registers, but that's about it. The best implementation of this USB stack that I could find was actually the secure ROM for the iPhone itself. So the secure ROM is kind of the boot ROM for the iPhone. It's the first piece of software that starts up. And you have access to the binary forms online. Like people have dumped the secure ROM from the iPhone and posted these binaries online publicly. So basically, I took one of these dumps that someone had published and I reverse engineered it to source to see, how does this thing actually operate? So that was quite painful, quite honestly. And at the end of this process, I reversed it close enough to source that I could re-implement it in C and get my iPhone to appear to my computer as this special KTRW USB device. Where you can see the serial number is Google Project 0. So this is definitely, not your normal iPhone USB stack. The final piece of the puzzle is implementing the GDB stub. It's pretty, straightforward. It's a bunch of string parsing and driving the debug hardware according to the ARM specification. Nothing too interesting there. And the end result of that is that I could finally connect to my iPhone over a regular USB cable and debug it in the kernel with LLDB and IDA Pro. And so you get this kind of, debug interface in IDA, which is pretty cool. Yeah. So let's look at a actual practical example of how this works in practice. So the actual demo I'm going to be giving is the out-of-bounds timestamp is a kernel bug that I found a while ago and wrote an exploit for. And it affects iOS 13.3. And so I'll demonstrate how I used KTRW to find this vulnerability in the first place. So this way I found it was actually somewhat roundabout. Can you read this? Yep, okay, cool. So there's this function, we're in the XNU source code in the IOKit kernel IO memory descriptor.cpp file. I was looking for virtual memory bugs, and I found that there's this piece of code in the function IO general memory descriptor memory reference create. And I thought, oh, this particular piece of code looks interesting. I wonder if this code ever has a particular value for the page protections that it's going to pass to a later function. So in particular, I wanted to know, at this point, at the end of this if block, what is the value of prot right here? And so the way I did this was I said, okay, well, I put all this effort into building a kernel debugger, might as well use it to find out, dynamically, does this situation ever occur where prot has one of these flags like map mem ledger tag network or map mem grab secluded. Do these flags ever end up in prot? So in order to do that, I pulled up IDA and I located the specific instruction that I said, prot is going to be in this variable at this particular point. So in the decompilation, you can see the same code as before, but just decompiled. Is this still readable to people? Yeah, okay, cool. So here you can see again, like purgeable, purgeable kernel only, tag network, skywalk. So all the same flags from the source, but just decompiled in IDA because I wanted the address of the specific instruction which I would be using to set a breakpoint. So I will switch over to LLDB. Let's make this a little bit bigger. Okay, so here we have a session connected to this phone. I don't have screen capture like Samuel did for this phone because once the debugger starts running, it's going to take over the USB hardware controller, and therefore you can't get any data off of the phone onto the laptop except via my special kernel extension. And so the demo will literally be, I start an app and it disappears. So not super interesting. Instead, I'll try to hold up the phone and demonstrate kind of visually. So I apologize if that's somewhat less exciting. So the first step is we're going to launch an app which does a kernel exploit, which should give us the ability to modify kernel memory and call kernel functions. Then I'm going to launch the kernel extension loader application, and that should launch, and then we should see some output from our proxy program. So you can see that we found a KTRW device and opened the KTRW device. And so now we can connect to it via LLDB. So GDB remote. All right, we have that. So we'll continue. So the phone is now running as it normally does. I'm going to actually reconnect so that it detects the kernel location. So we will halt and disconnect, and then add dsim, kc.symbols, and okay, now we're going to GDB remote again. All right, that's much better. So now we are connected to this phone. You can see that LLDB automatically detected the load address of the kernel and the kernel UUID and all of that. And you can see now that we're halted. If I try to interact with the device, it doesn't actually move. You can't do anything like that because it's actually halted. So now we're going to, I'm going to get the kernel slide. So, all right, so we have computed the kernel slide, and now we can compute the address of this function in kernel memory. So take that. So if I disassemble around this, X for I. All right, so we can see that this instruction, D40, LSR, W8, W88, and that's in fact the exact same instruction as here. So we do have the address of this instruction, and we can now set a breakpoint. And now just to make this process somewhat more speedy, I'm going to also make this a conditional breakpoint so that we only get the specific backtrace that we're looking for. So I set a breakpoint on this instruction, and I'm going to continue. And the breakpoint pretty much immediately gets hit. And now we can examine W9 to get the value of the flags. I saw, oh, this doesn't look like the flag values I was expecting. What I noticed when I did a backtrace was that the backtrace actually looked somewhat interesting. So I didn't actually end up triggering the behavior that I wanted, but in the backtrace, I saw kind of some interesting stuff that I hadn't observed before. And it's like, hey, let's explore around a little bit, see what's going on here. So in the backtrace, you can see IO user client external method. So this is an external method call to some sort of kernel driver. And in particular, you can see IOXL command queue, submit command buffers. So this is in the Apple Graphics Accelerator drivers. There's something called command buffer, which gets submitted to the graphics hardware. And kind of, working through the backtrace, I saw, okay, here's where we hit IO general memory descriptor. And let's get to the first point that we call out from the Apple Graphics to IO buffer memory descriptor is right here. And let's go to that in IDA. So we're going to print, oops. So we get the unslid address of that instruction and go there. All right, so you can see that we have just after the called IO buffered memory descriptor with options and IDA. And this is inside of a function, AGX parameter management physical, create parameter buffer block. So, every time I kind of see a new piece of code, I like to explore a little bit to see what's going on around here. And it actually really quickly caught my eye that, something looks kind of funky. So we have this array, which we are storing this new, so we're going to return from IO buffer memory descriptor, we return a buffered memory descriptor. We set that parameter here, and if that object was successfully allocated, we're going to store this param block phys object inside of this array in the AGX parameter management physical class. So this looks kind of sketchy to me because this buffmd count variable, which is used as the index, is, it's storing sequentially an item after an item and updating the index each time. But there isn't actually a check on this index anywhere within this function. Like, this is the only place that buffmd count is referenced. So that seemed kind of suspicious to me, like maybe if you get this function to be called enough times, you can overflow this array and write things out of bounds in the array. Cool, let's see if that actually happens. So I then kind of worked up the call stack. The next one was here, which is unslid address ending in E58. So I went to that address and saw, okay, so here we have the call to create parameter buffer block, as we expect. Still no checks on the buffmd count variable. Looked through all of this and kind of saw like, okay, yeah, it looks like it's usually taking these paths to function based on the state of the variables halted in the debugger. But still didn't really look like there was any checks going on. So then I went up one more layer to the function I called that. Oh man, it takes a while to decompile. And saw, okay, here we are. Okay. So here we have the code which it sets the next index, and it does actually look like it does some math to make sure that it's wrapping around in the array properly, so this doesn't actually look like a bug. So didn't end up finding anything here. But, I found this really new function. It's, huge, 1,000 lines for a single function IDA decompilation, so might as well take some time and explore, look what's going on. So to do that, you go to the top of the function, set the types of all the parameters correctly, and just see, how does control flow through this function. And kind of the first thing that you see at the very top of this function is, so this, one of the parameters of this function is this thing that I've called shared kernel command. This is a pointer to memory which is shared between user space and the kernel, so it can be modified at any point. And I noticed that, okay, if we have command type of 1001, then, we return immediately. If the command type does not equal 1000, then we do process segment kernel command, a different function. And then the whole rest of this function, all 1,000 plus lines, are just handling command type 10,000. So this looks kind of wild that there's this many processing steps going on. So let's see what the other processing steps might look like. Maybe there are 10,000 other 1,000-line functions which are worth looking into for bugs. And here's where I've actually found, this looks extremely problematic. So this is, again, a shared memory kernel command. And it's doing a check, kernel command type does not equal 2. Then it's going to do handling for command type of different than 2. And so we're looking for command type 2 in particular. We'll go down to the end of this if statement to see the processing for that. All right, so here we're processing this command from shared memory, and says, okay, so for command type 2, which is a KIOXL kernel command collect timestamp, we expect the command size to be at least 8 bytes, because if it's less than or equal to 7 bytes, we bail out with an error message. All right, sounds fair enough. What does the rest of the thing do if it is at least 8 bytes? Well, if it is 8 bytes, we're going to find offset 8. We're going to find offset 8 in the kernel command, and we're going to write a 64-bit output of mock absolute time to offset 8. Seems fine, right? If we have 8 bytes, then write starting from offset 8 to offset 15. Totally, totally valid. No, so this is actually totally problematic. So kernel command is, imagine that this is the last 8 bytes on a page of memory. Then writing at offset 8 will write the first bytes of the subsequent page of memory. So this is actually just looking at just these couple lines of code, very clearly an out-of-bounds write bug, and absolutely, totally exploitable. So yeah, not really what I was expecting to find when I looked into trying to find virtual memory bugs, but just taking some time to explore around, dynamic analysis can give you really, really deep call stacks. I would never have been able to reverse engineer through this entire call stack to get to that point just by myself, because it's a pain. It's a huge amount of code to reverse engineer. And the dynamic analysis can really help you jump right to the interesting points. I know this code is reachable because I have a live system which is stopped at this point in the code. So yeah, it opens up a lot of new attack surface that otherwise might not be reachable. Yeah, so that's kind of my demo for how I used KTRW to find the out-of-bounds timestamp bug. Cool. Yeah, thank you very much. I have the project on GitHub. It's called KTRW. I also have a blog post that documents, the process that I went through to find this bug. I will say that, it's kind of not super relevant maybe to a lot of you in a macOS security conference. The only tie-in that I can really offer is, right now, Macs are running Intel. Potentially, that may not be the case in a couple of years, and hopefully it won't be this difficult to get kernel debugging on your Macs in the future. So I'll leave you with that. Thank you very much.